Thinking Aloud. Conversations on the leading edge of knowledge and discovery with psychologist Jeffrey Mishlove.
Hello, I'm Jeffrey Mishlove. Today, our topic is Superstring Theory. This is another special remote interview recorded on Skype with my dear friend, Saul-Paul Sirag, a fellow without any formal advanced college degrees, but who is a master physicist and mathematician and author of the book ADEX Theory, how the ADE Coxeter graphs unify mathematics and physics. He's deeply into string theory. Now, this is an unusual interview. It runs almost 90 minutes. It's the longest one I've ever posted on the new Thinking Aloud channel. And furthermore, it is very technical. So if you haven't already watched the prior interview with Saul-Paul on physics and consciousness, I highly recommend that you do that. And in fact, if you look at the upper right-hand corner of your screen, you will see a link to it now. It'll well be worth your while to view that video before watching this one. But be prepared. It is a lengthy video. It is rather technical. We hope to make it enticing and interesting to the intelligent lay viewer. And if that's you, I think you'll get a lot out of it, even if you don't follow all of the fine points and nuances relating to string theory. And now I'll switch over to our Skype channel. Welcome, Saul-Paul. It's good to see you again. You know, people talk a lot about string theory, but I think the average viewer of my program is probably not well informed about string theory. We hear it as a buzzword all the time. It seems to be controversial. But why don't we start out by letting our viewers know why string theory is important in the first place?
Well, the main reason string theory is important is because it's the only known theory that we have today that is capable of unifying all the forces, all four forces, including especially gravity. It's very difficult to unify gravity with the other forces because, well, there are many reasons, but the main thing is that it's very difficult to create a quantum version of gravity called quantum gravity. Mm-hmm. And quantum gravity is something that physicists have been attempting to do for decades. But until string theory came along, every effort totally failed for various reasons.
Now, does quantum gravity, does that mean to find the smallest indivisible particle of gravity? Is that what that's about, a quantum of gravity?
Well, that's an important element of it, and what that element is called a graviton. Mm-hmm. A graviton, many decades before string theory, physicists like Richard Feynman had attempted to quantize gravity, and one of the things they discovered immediately is that the quantum of gravity would be something that is very different from the other quanta because a quantum of gravity would have to be what we call a spin 2 massless particle. Now, the electron, the photon is the fundamental quantum of light. It's what electromagnetism when it's quantized, is based on the exchange of photons.
Mm-hmm.
And a photon is what's called a spin 1 massless particle. So why does a graviton have to be a spin 2 massless particle? Well, it's because gravity has to be always attractive, whereas when it comes to the electrical force mediated by the photon, you can have both attraction and repulsion, as we all know. And so this was people like Feynman and other people working on this decades ago said very clearly that if we ever quantize gravity, we're going to have gravitons, these massless spin 2 particles, as the fundamental force carrier, so to speak.
You would think that if the electron has both positive and negative charge possibilities, it should be a spin 2, not the graviton.
No, well, you have to understand something about what we mean by spin 1 and spin 2 and spin a half. The spin a half is what electrons have, not spin 1. I said the photon has spin 1.
I see. So the spin is, but you've explained that the spin is related to charge somehow.
It's related to the possibility of there being both repulsion and attraction, and gravity always has to be attractive.
Okay.
According to general relativity, which is our basic theory of gravity.
Mm-hmm. General relativity is a very successful theory, I presume.
It has passed every test that we've thrown at it, and the tests, as equipment gets more precise, the tests have become more precise. It has not failed in any test so far, and also mathematically, it's considered a very beautiful theory, very satisfactory theory from the point of view of aesthetics and many other criteria that physicists like to dwell on when they think about their favorite theory.
Mm-hmm.
But it's a classical theory, and meaning that it doesn't obey the laws of quantum theory, which have these probabilities and the Heisenberg uncertainty principle related to that, and many other aspects that are very, very extremely different from a classical theory such as gravity. Now we have other beautiful classical theories such as Maxwell's electromagnetism, but we were able to quantize that by way of the photons that, in fact, Einstein's 1905 paper on photons was really the beginning of quantizing Maxwell's theory of electromagnetism. Mm-hmm. And of course, immediately after that, people said, "Oh, yeah, well," and Einstein himself tried to figure out how to quantize gravity. Of course, he wasn't doing that in 1905 because he didn't create his theory of gravity until 1915. But he and other people since 1915, that's a long time ago, more than 100 years ago, people thought, oh, well, we ought to be able to quantize gravity. Well, they all failed. Okay. Mm-hmm. Now, here's a very, very interesting fact about string theory that people who put string theory down don't realize. And that is, string theory is about, well, it starts out being about very, very tiny strings that are about not much more than a Planck length in size. And now Planck length is very small, about 10 to the minus 33 centimeters, which is about 10 orders of magnitude smaller than a proton. A proton is about 10 to the minus 13 centimeters in size. Mm-hmm. So you go down 20 orders of magnitude from the size of a proton and you get to a Planck length. And so you have strings, fundamental strings that are no longer than say 100 times bigger than the Planck length.
And
But
I presume they're called strings because they are one-dimensional.
They're one-dimensional objects. Now, before string theory, we have a very good theory that people like Feynman have worked on and developed to a high degree, called quantum field theory. Now, quantum field theory deals only with point particles.
Mm-hmm.
Okay, particles that have no size whatsoever, and so what we do in string theory, one of the moves that we make is we say, well, suppose this is not how string theory arose, by the way, but today, looking back on it, we can say, well, okay, let's replace the points in Feynman's theory with lines, very, very tiny lines, so small that we probably think of them as points, but they're not really points. They're just tiny, tiny lines, okay?
Mm-hmm.
But these tiny, tiny lines are doing things. They're spinning. There's that word, spinning. And they're by the way, they're spinning at the speed of light, okay, which is as fast as they can spin, and they're vibrating, and the vibrational states of the strings are basically harmonics, okay.
Mm-hmm.
Now, when you have harmonics, there's a basic harmonics, right? And then you have higher frequency versions of that basic harmonic, that basic vibration. Well, it turns out that the basic vibration. Oh, I should add that the idea of string theory was that the harmonics would correspond to what we were calling fundamental particles. Okay.
Mm-hmm.
And it turns out that one of these fundamental particles, in fact, the most fundamental particle in the series, has to be a spin 2 massless particle.
Mm-hmm.
Okay.
Which is what you earlier said that is what we're looking for when it comes to the graviton. Exactly.
Now, there was a period of time between when string theory first arose in about 1970 and 1974, when we knew that string theory required a massless spin 2 particle, and why didn't anybody in 1970 say, oh yeah, that's the graviton? Well, it's because of the strange environment in which string theory arose. String theory arose in the environment not of anybody thinking about gravity, but about the theory of the strong force, the nuclear force, the strong nuclear force.
Mm-hmm.
And it was able to deal with that area of physics somewhat successfully in the early 70s. In fact, people in Berkeley, I remember when we were at the fundamental physics group, people in Berkeley were talking about a spin 2 massless particle, presumably in the strong force region of energy, and it even had a name. It was called a Pomeron, named for a Russian physicist named Pomeranchuk. And people were looking for Pomerons. It would have to be a strongly interacting massless spin 2 particle. Well, people very quickly realized that there couldn't be such a particle, because if there was a massless spin 2 strongly interacting particle, we would have known about it ages ago. And at least 10 or 20 years before 1970.
How so?
Because it has very precise characteristics which would have shown up in the accelerator experiments that we were doing at Berkeley and elsewhere with the Bevatron in Berkeley. And at that time in the 60s and 70s, the Bevatron at Berkeley was creating new particles, every month, if not every week. I mean, it was called the zoo of particles, and it was tamed only by that zoo of particles was tamed by the quark theory of Gell-Mann. That's a whole other story. But anyway, it took until 1974 before a physicist named John Schwartz and Joel Shirk, a French physicist, to say, well, so we have this massless spin 2 particle fundamental in this theory. We should consider string theory as being fundamentally a gravity theory, not a strong force theory. Only secondarily or third hand would it be have anything to do with a strong force. Although it would have a great deal to do with a strong force, but in a very different way than it was first thought about. Anyway, so by 1974 is the first inkling that string theory had anything to do with gravity. But here's the strange thing. For 10 years, between 1974 and 1984, hardly anybody paid attention to this paper of John Schwartz and Joel Shirk. And just a year or two before 1984, Joel Shirk actually died at a young age. He was a diabetic and who ran out of insulin in some isolated place and died accidentally. And he was a very brilliant physicist. He wrote a lot of interesting papers. But John Schwartz at Caltech was able to get a British physicist named Michael Green to work with him on this idea that he had in almost 10 years earlier, 1974, and together, Schwartz and Green published a paper in 1984 proving that string theory was a viable quantum gravity theory, provided a certain symmetry was automatically brought into the picture. Now, there are a lot of other aspects of string theory that had to be obeyed. For instance, there had to be supersymmetry, which means that there has to be a pairing up of fundamental particles with particles of opposite spin. There's that word spin again. We have, so in other words, particles of half integral spin would have a partner particle, a supersymmetry partner, we call it, that would be spin 1, spin 0. In other words, it would have to have an integral spin, not a half integral spin, and that's called supersymmetry. And supersymmetric string theory requires a 10-dimensional space-time. That's another requirement of the theory. There's a whole raft of requirements that string theory has to be obeyed. And if you're a theoretician, you don't balk at these requirements, because each requirement hones down the possible structure of the theory and makes it more precise.
Let me step back for just a minute and recap, so that I'm sure give our viewers a chance to make sure they're following us. It seems as if what you're saying is they start with a postulate, which is they go back to Feynman's quantum field theory and say, what if instead of the particles being point particles, they are tiny, tiny little string particles? That'll be our starting assumption, and then we look at the mathematical implications of that and get all this other information that you're talking about, the spin 2 particle that's massless and all of the other requirements. They're derived mathematically.
Yes, what you're saying is a possible way that string theory could have arisen, but as I said, it has a very strange origin, and one could have arrived at string theory by making that postulate, but that's not how it happened. I can tell you more about how it happened, and it's very magical and strange, but that's probably too, wouldn't serve our purpose right now anyway. Okay. But I wanted to mention, I mentioned a very, very important word, which is symmetry.
Yeah.
That this string theory of Schwartz and Green had to obey a very specific symmetry, and that symmetry is called E8 cross E8. Now, what does that mean? The E8 group.
We're talking now about group theory, which we discussed in some detail in our previous interview.
Right, and group theory has everything to do with symmetry, and remember that I've mentioned also one of the things we talked about was the ADE Coxeter graphs.
Right, and E8 would be one of them.
Yeah, there are only three. There are an infinite number of A's and there are an infinite number of D's, but there are only three E's, and they're E6, E7, and E8.
Mm-hmm.
And they are in magical ways, according to my point of view, related to the Platonic solids. This is something I mentioned before. And E8 corresponds, for instance, to the icosahedron and the dodecahedron, and E7 corresponds to the cube and the octahedron, and E6 corresponds to the tetrahedron. So those three symmetry structures correspond to all five of the Platonic solids. Mm-hmm. But E8, when we say E8 cross E8, all we mean is that we're putting together two of these E8 symmetry groups, okay? And this is a very, very large group.
120 mirrors, as I recall.
Yeah, in what's called in Coxeter's what he calls them, as I mentioned before, are kaleidoscopes, and so this the E8 kaleidoscope has this 120 mirrors. Yes, and these mirrors actually would be seven-dimensional planes, actually, because if you're cutting an eight-dimensional space, you need a seven-dimensional plane to cut it in half, and to flip things from one side of the mirror to the other side, and vice versa. And the mirrors really are the heart of what's going on. The reflections in the mirrors, all those reflections create a reflection group called also a Coxeter group. And the Coxeter discovered all this stuff way back in around 1935. Well, he published his paper in 1935 when he was dealing with a mathematical type problem. He's a mathematician, which is to describe all possible hyperdimensional crystallographic structures. And crystallography is ultimately based on reflections. And anyway, back to string theory. So 1984 was when this paper was published, and it created a kind of bandwagon effect. That's when suddenly, rather than two or three string theorists in the world, okay, there suddenly became hundreds, and then in another decade, probably thousands of string theorists.
It's fair to say that today there are thousands of physicists working on string theory.
Yes. Yeah, throughout the world, not all in the United States, but most of them are in the United States, actually.
So that might be, I'm going to guess, maybe 10, 20% of all theoretical physicists.
I don't know how many there are a lot more theoretical physicists that work in different areas than string theory, but I would say that what's considered the cutting edge of theoretical physics is string theory. Now, you can work in theoretical physics. You can work in a lot of areas. Like particle physics, like the search, like the people that worked on discovering the Higgs particle. A lot more. Well, Higgs himself was a theoretical physicist, published his paper back in '64, and the Higgs particle was discovered at this huge accelerator in Switzerland near Geneva in 2012. So it took quite a while from when the paper was published to when the particle was discovered. It was, you needed a really big accelerator. So a lot of theoreticians are working on particle physics, not string. In other words, they're working on what's called quantum field theory. And I mentioned earlier that quantum field theory considers the fundamental particles as the really fundamental particles as being essentially point particles. Like a proton is not a point particle. Proton, as I said earlier, is about 10 to the minus 13 centimeters, but it's made up of quarks and gluons that glue the quarks together, so to speak. It has 3 quarks, what we call 2 up quarks and a down quark. But those entities, the gluons and the quarks, are considered fundamental. And in quantum field theory, they're considered points. Okay. No bigger than a point. Now, here's a very interesting aspect of string theory that should be taken into consideration, and that is that because quantum field theory deals with point particles that have no size, there's a mathematical problem, and because of a very important law called the inverse square law, because the inverse square law says that forces fall off with the square of the distance.
Right.
So that means if you have 2 point particles and they meet, okay, the interaction is going to be at infinity, right? Because of the inverse square law. So when things get farther away, the force falls off, but when they get closer, the force keeps increasing, right? So,
of course, if they occupy no space at all, how can they ever meet?
Yeah, but okay. Well, the person who dealt with this problem probably most effectively was Richard Feynman, and the famous Feynman diagrams are simply lines, right? That lines meeting at a point. Okay. And those are what we could call the world lines of the particle interactions. Okay. Now, of course, Feynman was very aware. Other physicists were very aware of the problem that of these infinities, and a lot of work has been done in quantum field theory to get rid of these infinities, including Feynman's work. Well, but if the fundamental things are not point particles but are strings, guess what? When 2 strings interact, and they do interact, when they meet, they don't meet at a point. They meet at a finite, at some finite distance. So guess what? You don't have that infinity to deal with. That a lot of mathematical work. By the way, the mathematical work that goes into getting rid of the infinities is considered illegitimate by mathematicians. By the mathematicians, they look askance at what the physicists are doing. The physicist says, "Well, it works. We make predictions, and the predictions come out, so we trust it." But the mathematicians don't trust it. Because they have higher standards, let's say, of precision. They I mean, in mathematics, you prove theorems, and there are very few theorems proved in physics. I mean, there's the famous Bell's theorem. That's a theorem. There are very few theorems in physics, but that's, but in mathematics, people say that a mathematics paper has theorems in the same sense that a story has sentences.
Mm-hmm.
Okay.
Well, physics is an empirical science, and mathematics is a logical discipline.
Yes, but they're very closely related because over the years, a lot of mathematics has been discovered by trying to solve physics problems. Like Newton, for instance, created the calculus to deal with gravity that he was interested in describing, and so on. I mean, many, especially in the 19th century, many mathematicians were also physicists and worked on both sides of the issue. They're very closely related. And now string theory, because string theory has come up with so many different new mathematical structures, the mathematicians have gotten probably more interested in string theory than physicists in general. I mean, the mathematicians don't care like the physicists do, as you said, about empirical results. What they care about is mathematical structures, and they see these new mathematical structures that they can study now with the tools of string theory.
And in your book, ADEX Theory approaches string theory as a mathematician.
Yes, the subtitle of my book, ADEX Theory book, is how the ADE Coxeter graphs unify mathematics and physics, because it's really a way of seeing that they're just two different sides of the same coin almost. Now there are a few empirical results that have come out of string theory.
Before we go into that, just let me ask one question, because we started out by talking about the graviton and how the spin 2 massless particle could be a graviton. Is it now accepted that string theory has been able to identify gravitons?
Identifying graviton, yeah, certainly the theory says that. Now, to detect gravitons as a fundamental particle is another story. The problem is that the force of gravity is incredibly weak compared to the electromagnetic force. It's like 40 orders of magnitude weaker than the electrical force. The electrical and the strong force is stronger than the electrical force, even somewhat stronger, a couple of orders of magnitude maybe. But when you have this 40 orders of magnitude difference in strength of the gravitons, what that 40 orders of magnitude difference means is that it's 40. It's so much less likely that gravitons will interact. Okay? Gravitons interact with mass. It's mass. Right. Any two masses, according to this theory, are exchanging gravitons. That's what accounts for gravity in the graviton theory. And so it's much less likely than that two masses will exchange a graviton. So they'd be very difficult to detect as fundamental particles. They're required by string theory simply because that vibration corresponds, a certain vibration of string theory corresponds to such a particle. So string theory requires it, but we certainly could detect gravity, but we detect gravity because detect gravity because there's so much mass around.
Yeah.
Like the mass of the Earth, the mass of the Sun, and so on, to deal with. So, given plenty of mass, you will detect gravity, but not the graviton as a fundamental particle. I don't think the graviton as a fundamental particle will ever be detected in you have to have an accelerator bigger than a galaxy, let's say. Okay.
That's awful big.
We're not going to build anything like that. And in a way, there'd be no point because we can test the theory in other ways than finding the fundamental particle. Now, one very important question is, well, what about Einstein's theory of gravity? Does string theory have a way of making Einstein's theory of gravity a subtheory? And the answer is yes. Yes, that's what the string theorists are claiming over and over again. And it's true. I would say it's true that Einstein's wonderful theory of gravity is just what we call the classical limit of the string version of gravity theory. But not only that, we have a way of bringing in all the other forces, and I would claim that my ADEX Theory book actually brings in another way of doing this that is related to what the other physicists in string theory are doing and bringing in describing the other forces, but I have a finite group called the S4 group, or it's the symmetry group of the octahedron. So it's called the octahedral group, and that group is actually the starting point of my approach to unification of the forces and to string theory. That's spelled out in great detail in my book, and actually that's spelled out in some detail in the appendix paper that I wrote for you, Jeffrey. That's all in there too, in great detail. Now, do you want me to go into what I consider a verification of prediction of string theory?
Yeah, I think that's important because up until now it's been basically mathematical extrapolations.
Yeah, but mathematical extrapolations that have to obey a plethora of consistency requirements and a whole list of things that have to be true of the theory, that it's a mathematical test rather than an empirical test. Sure. But okay, let's talk about an empirical test. Okay, there was a very interesting experiment that was done on Long Island at the Brookhaven National Laboratory, where they were firing gold atoms at each other at very, very high energy to create what they called a quark gluon plasma. See, because I said earlier that protons are made up, and neutrons too, are made up of quarks and gluons, and that's what's inside the nucleus of a gold atom. The gold atom has 72 protons and a whole bunch more neutrons. And so if you bang these gold atoms together at high enough energy, the idea is it breaks them apart, and the idea is that the quarks and the gluons would come out very, very briefly for a fraction of a second, but they had a way of measuring what what certain characteristics they would find. Now, what the particle physicists at Brookhaven were predicting was what they called a quark gluon plasma. What a plasma is in that sense, is an ionized gas. Okay, and in other words, a gas, something that functions as a gas, but it's made up of charged particles, so it's like an ionized gas. Well, before the results were in, some string theorists did a calculation to see what they thought would occur, and using a very, very exotic aspect, one of the most exotic aspects of string theory, which I won't go into detail because it's very complicated, but let me just say that using a very exotic aspect of string theory, they made a calculation that what the Brookhaven people would see was not an ionized plasma, but rather something more like a liquid that was extremely, extremely non-viscous, extremely, much lower viscosity than water. Say water has low viscosity has to do with stickiness. Okay, and say water has very low viscosity, but say honey has high viscosity. Okay. So honey is sticky, water is not. Well, what they predicted was that what the Brookhaven people would see, rather than a quark gluon plasma, would be a very, very non-viscous liquid, actually. And lo and behold, that is what they saw. They saw what the string theorists predicted, not what the particle physicists predicted. Okay. So that for me is a verification of string theory.
And I assume there are probably several others.
Yeah, there are others. A physicist at the University of Michigan, for instance, before the top quark was discovered. The top quark is a very heavy quark, and it wasn't discovered as a particle in particle accelerator experiment until 1995. But before that occurred, he using string theory predicted a very high mass for the top quark, and what he predicted turned out to be right. Now this was he wasn't the only one making predictions. Prior to his paper predicting, there were other people predicting the mass of the top quark. In fact, a very prominent European physicist not only predicted the mass of the top quark, but claimed that it had been discovered at CERN at a much lower mass than this guy in Michigan was predicting. But he was not only claiming a prediction, he was claiming that it was found. This was years before 1995. When it was found in 1995 at an accelerator near Chicago called the Fermi National Accelerator, it was found there in 1995. That's the last big result to come out of that accelerator, because it's been totally superseded by a much bigger accelerator at CERN now, the Large Hadron Collider. But this is another case of a prediction based on string theory of a particle, and it was the mass was so high that it was almost unbelievable that it would be that big, But the guy turned out to be right, and the guy in Europe who claimed that it actually been found at a much lower mass turned out to be wrong. So these kind of fights go on all the time, and that's what keeps physics honest, so to speak.
Mm-hmm.
So string theory has a lot more going for it than that, because as I mentioned earlier, of all the mathematical structures that arise in the context of string theory, that's gotten the mathematicians excited about it. And I write about this at great length in my ADEX Theory book. And the reason I write about this is all these strange mathematical structures that related to string theory. Here's the punchline: they're all classified by the ADE Coxeter graphs.
Mm-hmm.
That's the point of my book. And so the ADE Coxeter graphs are really the unifying principle underlying this unification. See, in other words, there's not just unification of forces going on in physics. There's unification of mathematics going on in mathematics. It's been going on for decades as more and more structures have been brought into the classification scheme of the ADE Coxeter graphs. Maybe I should mention at least something about what a classification scheme really is. It's what the kind of thing mathematicians love to do, which is, like I mentioned earlier, that Coxeter's work back in 1935 was to mathematically describe all possible crystallographic structures in spaces of any number of dimensions. That's a classification scheme, okay?
Right.
So mathematicians working in many other areas work out ways to classify all the objects in whatever area they're working on, that they're fundamentally interested in.
Mm-hmm.
And it turns out that these same graphs, these ADE graphs, classify all kinds of other very, very different mathematical structures.
Mm-hmm.
And so, in other words, the ADE Coxeter graphs are a way of unifying all these different fields of mathematics, and unifying them in the sense that not only do the graphs classify them, but the graphs provide a way of transforming from one type of mathematical object to a very different type of mathematical object that you would never guess ahead of time that had anything to do with each other. They don't look like they have anything to do with each other, but they do. And so in other words, because string theory uses all of these that have been found so far, 20-some different mathematical structures, they all correspond to aspects of string theory.
Well, when we spoke in our first interview on physics and consciousness, you mentioned something called M theory, which I guess stands for membranes. It seems to be maybe a more advanced edition of string theory because it unifies several different variations of string theory.
Yes, that also happened in that magical year of 1995, by the way. Mm-hmm. And it was due to mainly to a physicist named Edward Witten, who's a very brilliant guy. I met him once or twice. And string theorists consider him, the leader of the pack, so to speak, as a theoretician. And he's also the only physicist who's gotten the Fields Medal in mathematics, which is the highest honor in mathematics. The only physicist ever to get it for work that he did using physics to solve a certain problem in knot theory in mathematics. Okay, he got the Fields Medal for that work. And anyway, in 1995, he found a way of unifying the 5 different competing versions of string theory. All 5 of these string theories were published between 1984 and 1985. Yeah, all 5 of them, and each of them have a way of saying, "I'm the true string theory." So if you have 5, one for each finger, okay. different guys saying, I'm the right one, pick me. Well, that's not a very good situation to be in. And so people like Witten worked on the problem. And one of the aspects of the problem that made it solvable was the fact that you could not only have strings, but you could have larger objects called membranes, and membranes can be of various dimensions. An ordinary membrane would be a two-dimensional version of the string. The string would be a one-dimensional membrane, so to speak. You can have membranes up in a 10-dimensional space-time. You can have membranes up to 9 dimensions. Okay, nine-dimensional membrane. So Witten called his unification of the 5 competing string theories M theory, but he always says that, well, M stands for magic, mystery, or membrane according to taste.
And I also noticed a book of which Witten was the co-author called Superstring Theory.
Well, Superstring Theory is, I actually mentioned it earlier. I said strings have to obey a symmetry called supersymmetry. Mm-hmm. And superstring theory is the theory that uses these kind of strings. Mm-hmm. Superstring theory goes way back to about 1971. Okay,
so membrane theory is an advancement over superstring theory.
Well, it contains superstring theory as sub-theories, and these 5 competing string theories are all superstring theories. Mm. In fact, 2 of them are called heterodox string theories because they actually put together the 10-dimensional superstring theory with the 26-dimensional what's called bosonic theory, which does not, in bosonic string theory you don't have supersymmetry partners, and which was the 26-dimensional string theory was the first theory that was discovered, but the problem was that you could only have particles with integral spin. Well, that's not what we want. We want to have a theory that has both integral spin and half integral spin. And immediately, somebody said, well, let's roll in a symmetry, call it supersymmetry, and we'll have a partner for every particle, and then we can deal with it. Mm-hmm. Now, this is the reason they could think of something like that is because something like that had already happened way back around 1930 when Dirac unified quantum theory with special relativity. But in order to unify in order to unify quantum theory with special relativity, it turned out that he had to allow every particle to have an antiparticle partner. Hmm. Okay, and lucky for him, only a few years later, the first such antiparticle was discovered. That was the anti-electron called a positron. Mm-hmm. And in 1955 at Berkeley, the antiproton was created in the accelerator, and it took until 1955 for physicists to decide that the antimatter idea was universal to particle physics, because by then we had 2 particles, the anti-electron and the antiproton.
So this is another example of where Dirac predicted these particles based on mathematics, and then it was confirmed empirically.
It was confirmed empirically, really accidentally, by a guy named Carl Anderson, who hadn't even read Dirac's paper, and later said that if he had read it, he wouldn't have even understood it because it was a theoretical paper. And, they don't read each other's papers, actually. They're so different. But anyway, so that was lucky for for Dirac that his theory was confirmed, or at least partly confirmed that early. There was still a lot of speculation that, well, it might be true for electrons, but for any particle, that's a little bit hard to swallow. But by 1955, when the antiproton was created at Berkeley in the Bevatron, in fact, the Bevatron was built with a certain energy level to do that, actually, to create the antiproton and the antineutron, which was also discovered, by the way.
Bevatron stands for billion electron volts.
That's correct. It was set at 6 billion electron volts, I believe.
Yeah.
And that was the biggest accelerator in the world at the time it was built, and for a few years after. But anyway, so the thing is that looking back at what Dirac did, well, it wasn't too big a leap of faith for some other physicists to say, well, that worked for Dirac. Let's try the same game over again. This time, notice what there's a beautiful parallelism here, though, because Dirac was unifying quantum theory with special relativity, and that required the existence of a new type of particle called antiparticle. Now we're attempting to unify quantum theory with gravity.
With general relativity.
With general relativity, and lo and behold, in order to do that, we need to also double the number of particles all over again to have supersymmetry partners for all the particles. So I regard that parallelism as being very telling, and from an almost mathematically aspect of the beauty of the thing, that it's very compelling. But the thing is that in order to verify the theory, we have to find these things, and we haven't found any supersymmetry partners yet. But the theory says they must exist, and not only that, but for like the graviton, depending on the type theory you have, you can have several different gravitinos. They're called the spin 1/2 version of the graviton, and it depends on the type of symmetry that you're using, actually, that determines the number of gravitinos that you'll have in the theory. I could go into other far out aspects of string theory that have beautiful, very strange mathematical structures associated with them. You may have heard of the monster group, for instance, and Monstrous Moonshine associated with the monster group, and it turns out that that's very, very much related to string theory.
Yeah.
In fact, I could go into some detail on what the monster group is, and Monstrous Moonshine, and so on. Monstrous Moonshine was called that because the predictions that the mathematicians made about this group was so outlandish. Moonshine. I mean,
well, have they been confirmed?
Well, first of all, if you're a mathematician, you want to know whether the Monstrous Moonshine conjectures have been proved.
Yeah.
That's if you're a mathematician, you want proof. Okay?
Right. Okay.
So here's the punchline. Monstrous Moonshine was proved by a guy named Richard Borchard, who's now a math professor at Berkeley. He did this as a graduate student, or shortly after, maybe as a postdoc at University of Cambridge. And guess what? In order to prove Monstrous Moonshine, he had to use string theory. Okay, that's my punchline. So see, that's an example of the unification of mathematics and physics. Because in mathematics, Monstrous Moonshine is considered the most far out thing in the field. Okay? In the whole field of mathematics, Monstrous Moonshine is by far the strangest thing, and it took some very strange. Well, the guy who thought it up mainly was John Conway, who's a very interesting mathematician. He was at Cambridge, and then he's been at Princeton. I think he may have died recently, but anyway, he was at Princeton for a long time, and Portrait was his graduate student. Okay. And he finally found a graduate student that could prove his conjectures. Yeah. Okay. Which is typically what happens. Monstrous Moonshine is proved as a mathematical theorem. That's as good as you can get.
I see.
But in order to do the proof, Portrait had to use string theory in order to do the proof. From my point of view, that's as good as it gets, in thinking of the relationship between mathematics and physics. Each chapter of my book deals with a different strange and sometimes not so strange aspect of mathematics. Like, for instance, I have a chapter on Heisenberg algebras. Well, Heisenberg algebras are, old hat to mathematicians, but physicists think of Heisenberg algebras as due to Heisenberg's uncertainty principle and the non-commutativity of certain variables in quantum theory, like position and momentum, and because space is three-dimensional, the Heisenberg algebra is seven-dimensional. The original Heisenberg algebra is seven. There's three dimensions of position and 3 dimensions of momentum and a dimension of Planck's constant. Okay. But if you're a mathematician, you ask this question: well, can I classify all possible things like that? Call them Heisenberg algebras in high-dimensional spaces. And guess what? They are classified by the ADE Coxeter graphs. Every Heisenberg algebra corresponds to one of those in very beautiful mathematical ways, by the way. Done by a guy named Koss, now fairly recently, like in 1980s or something. And so that's in my book. And I'm just throwing out examples of very different mathematical structures that are classified by these ADE graphs, but the graphs provide a way of transferring from one type of mathematical object into another. And so I think of each of these classification schemes, and 20-some schemes, are different windows to some underlying structure, which is in some sense the fundamental reality.
And the fact that they all fit together like interlocking pieces of a puzzle impresses you that there's a certain underlying Platonic logic.
Well, yes. The thing is that in my book, I propose that the ADE graphs themselves be considered Platonic archetypes. Right? I use exactly that phrase, Platonic archetypes, and they are Platonic archetypes, I think. When one looks at the graphs, I guess you're gonna have some picture of the graphs at some point.
Easy to show. Yeah.
When you see the graphs, you will see that they are very simple. Okay. Now there's a somewhat non-simple aspect about them that I need to explain, which is the graphs are simply a set of nodes with lines attached to them, right?
Yeah.
But the line means something, and it means different things in different contexts. But in the basic context, what that line means actually is a 60-degree angle between the mirrors, because these are Coxeter mirrors, Coxeter kaleidoscopic type mirrors, and so each node corresponds to a mirror, and the line between the nodes for all these graphs, for all the ADE graphs, corresponds to a 60-degree angle between basic mirrors. Okay? But the graphs can be interpreted in different ways, and that's how you transfer from one type of object to another type of object.
And I presume these 60-degree angles are through higher dimensions of space too, not just 3 space.
Oh, absolutely. Yeah. Well, as soon as you get beyond 4 nodes, you're into 4-dimensional. If you have 4 nodes, you're into a 4-dimensional space. If you have 5 nodes, you're into a 5-dimensional space, and so on. And remember that there are an infinite number of A's, an infinite number of D's, and 3 E's, E6, E7, and E8. And that tells us that 6 space, 7 space, and 8-dimensional space are special in some sense.
Yeah.
Those graphs make those ADE those E6, E7, and E8 graphs make those dimensions very special.
Right. Now, you published a paper in Nature many years ago on why there are only 3 fermion groups.
Fermion families.
Fermion families, yeah. And is that related to E7, 8, 6, 7, and 8?
It's related to E7. Yeah, the starting point when I didn't know about the string theory stuff, but I published that in 1982 originally with the title "Why There Are 3 Fermion Families," and I was just using the octahedral group as the basis for that claim. Okay, then later on, I came across the work of a very interesting mathematician in Canada named Mackay, M-C-K-A-Y. He talked to him on the phone. He insisted I should pronounce his name Mackay, not McKay.
Yeah.
But it looks like McKay, of course, to us. Anyway, he showed, he created an ADE classification of certain Lie group and Lie algebra structures that immediately made a connection between these structures and the Platonic solid groups and other things. But so I saw through Mackay's classification scheme, ADE classification scheme, that E7 had to be related to the octahedron. That's how that connection was first made, but by way of Mackay's classification scheme. And so actually he basically uses finite subgroups of a 3-sphere, which is also a group, by the way. It's called SU2, and so SU2 is of course a group with an infinite number of elements, but it's as a geometry, it's a 3-dimensional sphere, and so there are finite subgroups of this infinite dimensional group. Not infinite dimensional. I mean infinite number of elements in SU2, and the thing is that those finite subgroups are ADE classified, and so I actually call those groups were known about before, but what was not known was that they were ADE classified. And so I actually call in my book, in my papers about it, I call them Mackay groups. and one of them is related to E7, is the octahedral group, which is actually in Mackay's thing, it's the double octahedral group, and which the octahedral group is a subgroup. Anyway, that's how the connection between the Platonic solid groups are related to the E6, E7, and E8 is by way of Mackay correspondence. Mackay correspondence, which is a very interesting thing, which would be I write about it both in my paper, in my book, and it's in Jeffrey's appendix paper, the paper I wrote for Jeffrey's appendix called Consciousness: A Hyperspace View, by the way. And in my book, I don't go into consciousness very much at all, but in the paper, the appendix paper, it really concentrates on the consciousness aspect of the whole picture. So I regard the appendix paper in my book as being complementary in that sense. And to get the whole picture, you really need to read both. And of course, I refer to that. It's one of the bibliographical references in my book. I refer to my appendix paper in Jeffrey's book, of course.
Well, let me ask you this, though. Now, you predicted in 1982 that there would never be more than 3 fermion families.
Correct.
And
yeah.
Looking back...
And in 1982, we did not know whether that was true or not, by the way. So I was sticking my neck out, for sure. In fact, I remember a few years later coming across an article in Scientific American which claimed that the fourth fermion family had been discovered at some accelerator. And so, of course, I was very worried whether that would hold up. But it turned out that was a mistake, that discovery turned out to be a mistake. And we're quite sure now that there are only 3 fermion families. But certainly in 1982, when I stuck my neck out with the title, "Why There Are 3 Fermion Families."
Yeah. And so the idea, that prediction that you made was based strictly on the mathematical logic that you saw in the E7 group.
No. I wasn't into the E7 group. It was only into the octahedral group.
Okay.
Based on the octahedral group alone. I didn't know anything about in 82, Mackay hadn't even published his paper yet. Mackay's paper was published in 89 and 90, actually.
But the octahedral group is classified by E7. Isn't that what you said?
Yeah, but it's classified by E7 only by way of the Mackay correspondence. See, the Mackay correspondence was published in 89, I believe. So in 82, I hadn't even heard of Mackay. Okay?
All right.
In fact, the way I came across Mackay's work is very interesting because as you know, I was very, very fond of Coxeter's work, and Arthur Young was the first one that turned. That's my phone ringing. I can just take it off. Okay. I'll just take it off. And at the Institute for Study of Consciousness, where Jeffrey and I were starting in 1973, one of the first things that Arthur Young showed me was a book called Regular Polytopes by Coxeter, published originally in the 30s, but this was a later edition. So I got very interested in it was all about finite group theory and his classification schemes and so on. I came across a book in 1990, or maybe 91, probably 90, which is what's called a Festschrift. In other words, a celebration papers.
Mm-hmm.
Festschrift means paper feast, German word, where colleagues of a particular professor read papers in his honor, and he's there, and he might give a paper himself. And this was for Coxeter's 70th birthday, I believe.
Mm-hmm.
And one of the papers in that Festschrift was by Mackay, and it was about the Mackay correspondence that he had discovered. Otherwise, I wouldn't have heard about it for a long time. But that really interested me, because that was a way that I could see that the octahedral group, which I knew a lot about, which I'd written papers on, was related to E7. Here's an interesting thing about E7. Remember, we've mentioned E6 and E7 and E8, and E8 plays a big role in string theory. But what they do with E8 in order to unify with the other with all the other forces is to project E8 down to smaller groups, and they typically skip down to E6 and then to D5 and so on. And D5 is actually a well-known grand unified theory for unifying the forces, by the way. So once you get down to D5, you're into familiar territory of the particle physicists, at least the theoreticians. And by the way you project down is very simple in terms of the Coxeter graphs. You just remove nodes, because the way that Coxeter graphs stack is the lower dimensional structures are implicit in the higher dimensional structures, and the same goes for the symmetries and the groups and everything involved. It's like dimensions of space time. Higher dimensions contain the lower dimensions as projection spaces. So the thing is, they skip over E7 for certain technical reasons. But here's something interesting about M theory. We mentioned M theory earlier, that it was Ed Witten's way of unifying the 5 competing string theories in an overarching theory. But that overarching theory is an 11-dimensional theory, by the way. And it's not a 10-dimensional theory. But Witten also points out that the so-called low energy limiting group, limiting structure of M theory is something called 11-dimensional supergravity. Okay. Supergravity is a point particle theory. This is a point particle theory. Supergravity was actually in 1976. Now, remember, I said that there was this hiatus between 1974 and 1984,
right.
When nobody was paying attention to string theory. Well, one of the reasons is that a point particle version of supersymmetry was created, which was called, by the way, supergravity. It claimed to be a theory of gravity, and there was a lot of excitement about it. And it's actually a sub theory of string theory, because it's when you reduce the strings down to points. What you get is supergravity theory, but the thing is that 11-dimensional supergravity theory, which, as I said, is the low energy limiting theory of M theory. Okay, but people had worked on, because of supergravity, people had worked on 11-dimensional supergravity theory, and what they discovered was that the fundamental symmetry of it is, guess what? E7.
Mm-hmm.
Okay? And the reason for that is very straightforward. The reason for that is that 7 dimensions of the 11-dimensional theory are taken up by a 7-dimensional torus, and that 7-dimensional torus is actually a structure within the E7 Lie group. It's called a Cartan subgroup. It's the maximal commutative substructure of a non-commutative group. And
a torus is a donut-shaped geometrical figure.
And it can, and you can have ordinarily the torus that you're talking about is a 2-dimensional structure, right? It's got you go around one way and you can go around the other way, right? Mm-hmm. To characterize every point. Well, the thing is that mathematically we consider the torus as a product of 2 circles, okay? Mm-hmm. One circle going around one way and one circle going around the other way. But the thing is that from a mathematical point of view, you can have toruses of any number of dimensions. So you can have a 3 torus or a 4 torus or a 5 torus. It's just a product of more and more circles, in other words. And you create higher dimensional toruses that have the lower dimensional toruses as projections. Mm-hmm. Okay, so one has a 7-dimensional torus in this 11-dimensional space, and guess what? What's left is 4 dimensions, right?
Right.
Because 7 plus 4 is 11.
Right. Normal space-time.
Yeah. So that's how E7 comes into the picture. Mm-hmm. You see, by way of the commutative substructure of E7. But more than that, E7 provides a way of describing the symmetries of the particles and what kind of particles you're going to see and so on. So it's another way of unifying the forces, and it's the one skipped over in the usual way in string theory of going from E8 to E7 and to E6 and skipping over E7. But now E7 comes back into the picture by way of the M theory, 11-dimensional M theory, having this 11-dimensional point particle theory, where E7 plays a fundamental role. Okay, I was very happy about that development. Of course.
Saul-Paul, we've been going on now for nearly an hour and a half. I think this might be a good place to pause, and we'll come back to this discussion because I know it's like infinitely complex, and we could take it in many, many different directions. But I think at this point our viewers are probably going to need a little time to digest all of this.
Yes, and they would do well to take a look at the appendix paper, which is available to them, I believe.
Yeah. I'm going to link to it right now. We linked to it in the previous interview, and I know you and I have many, many more things to talk about, especially since you're writing your memoirs at this point and reflecting back.
I've gotten up to 1978 only so far, but a lot was happening back then.
Indeed, a lot was, and I know we shared many different adventures back in those days.
Yes. And I should add that the appendix paper has lots of diagrams, which will make a lot of what I'm saying a little bit more understandable. Diagrams are useful.
Mm-hmm. Well, thank you once again, Saul-Paul, and I look forward to talking to you soon. And
okay.
I thank our viewers for being with us as well.